Hello, everyone, and welcome to our special astronomy lecture this evening. Tonight's collaborative effort is between the Southern Vermont Astronomy Group, SAVERA, the Dublin School's Perkin Observatory, and Middleman Observatory at Middlebury College. For SAVERA, this is their monthly meeting. We welcome the Dublin School into the mix, and for Middleman Observatory, this is the third installment of our Middleman Astronomy Lecture Series. We are very fortunate to continue with this virtual forum tonight in order to extend the accessibility and reach of this talk. In addition to members of SAVERA and students at Dublin, we have other astronomy and space-curious individuals and amateur astronomers from New England and beyond, including other high school and college students from the region. In addition to numerous Middlebury students, we have Middlebury community members, Middlebury faculty and staff, and some Middlebury alumni, and some faculty and students from Middlebury's partner institutions in the Keck Northeast Astronomy Consortium. My name is Jonathan Kemp, and I am with the Middleman Observatory under the dark skies here in the Champlain Valley of central Vermont. After a few additional notes, I will then pass it off to Pat Porch of SAVERA to introduce tonight's speaker. At the end of the evening, Eric Schmidt of Perkin Observatory will handle questions and answers from the audience. I would also like to briefly mention some technology notes and rules of the road. This lecture will be recorded, but attendees do not have video enabled and will only potentially have audio enabled for questions at the end. If you have technical questions, please use the chat function to connect with our panelists who are hosting this evening. If you have astronomy or other subject matter questions for the speaker, please use the Q&A function. You can also upvote questions or comments from others in the Q&A area if you'd also like to see them addressed after the lecture. You may also ask a question verbally at the end of the lecture using the raise hand capability within the participants window. Chat, Q&A, and participants functionality should all appear on the edge of your webinar window. While we are very happy to welcome students of all ages, minors and other younger students should seek permission of a parent or guardian before participating in this evening's lecture. Lastly, please remember to share respectfully and with civility as we begin tonight's talk as a community. Now, I would like to introduce Pat Porch of SAVERA. Pat?
Thank you, Jonathan. Welcome, everybody. Thank you for joining us tonight. Hope everybody's staying healthy out there. I'd like to take just a moment to recognize a couple of people that make tonight possible. Jonathan, you've just heard from, handling our technical aspect of things. Eric, you will hear from afterwards to handle the Q&A. And most importantly, SAVERA member Jenny Sidja, who did the initial legwork to make tonight's speaker possible. So our speaker tonight brings us a wealth of education experience in astronomy. He studied under Carl Sagan, he's worked as a researcher at MIT, and went on to join the faculty at Wellesley College, where he's a McDowell Whiting Professor of Astrophysics. He's a planetary astronomer and had the pleasure of being part of the Cassini mission from its beginning to its end. Tonight, he will share his amazing journey with Cassini. At this point, I'd like to welcome Dr. Richard French to our virtual stage. Dr. French, thank you for joining us.
Thank you very much, all of you. I'm really delighted to be here today. I was born in Vermont. I've been in New Hampshire many times. So to have a real New England flavor to this talk and the audience is a real treat for me, even though I can't be there in person. Let me share my screen and get started. Just want to make sure somebody can give me a hands up and say you can hear me. Terrific. Well, welcome, everybody. I want to tell you tonight about an insider's view of what it's been like to be part of a mission that has lasted literally 3 decades. I got a call from NASA headquarters, or from NASA, in early 1990 saying, Professor French, congratulations, you are a member of the Cassini radio science team. Welcome to Saturn. And I had little idea of what that was going to involve. I had no idea at the time that it would involve efforts for lasting roughly 30 years. And in the brief time I have tonight with you, I want to give you just a sense of what it was like to be part of this extraordinary adventure.
T-minus 15 seconds. T-minus 10. 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. Pitch program is in. Roll program is in. We have cleared the tower, and the Cassini spacecraft is on its way to Saturn.
Now, I'd love to be able to tell you about the story of being at the launch 7 years after the mission began. But the true sad story is that I went down to Cape Kennedy to see the launch, but it was delayed by 2 days. And as a young professor, I felt such an obligation to go back to campus and teach astronomy for my introductory class that I missed the launch. I was told later it was a religious experience. I think the class would probably have forgiven me if I had stayed. But just picture of Saturn and its system tells you what a wonderfully rich environment it is to go to explore. Not only the beautiful rings, the whole host of planets here. If you learn all these names, you're basically fluent in classical Greek by the time you're done. Each of these moons has a story. Saturn is one of the giant planets, is a representative of the outer solar system. And just to get a sense of how giant it is, here's a rare alignment of the Earth, Moon, and Saturn to show you that to scale, really, it is an enormous system. And the spacecraft itself is about the size of a bus. It took 7 years to design and build the spacecraft. Partway through, NASA's budget got nearly cut, and we had to redesign the spacecraft at the end in a way that I'll describe, that had a real consequence for the kinds of observations that we could do. And if you look, you'll see to the left-hand side of this, there's sort of a gold foil-covered circular dish, which is the other part of this mission. This is really the Cassini-Huygens mission, and that was the probe to land on the moon Titan that I'll be describing later. Now, everybody talks about rocket science and space-age technology as though it's the most modern thing, but I want to remind you that when this mission was designed, the Mac Classic at the upper right was the computer that was the most advanced computer we had on our desktop. That funny little cord and a mouse was something we were just learning to use. The Apple Watch at the upper left had a knob. And at the lower right, the disaster of the century, we were told, was the Exxon Valdez oil spill. Who wants to send something to space that hasn't been tested already? So the technology that was used for the Cassini mission was really decades and decades old by the time it got to Saturn. And here's an image taken from our campus of Saturn behind the limb of the moon at the time. And either the planet is small or it's pretty far away. And one of the challenges of the Cassini mission is getting out to Saturn. I've already mentioned that it took 7 years to get there, but that took some stealth and some sleight. So this is my first opportunity to teach you some NASA jargon. This is an overhead view of the inner solar system. And you can see at the left, it's marked launch, 6th October, 1997. That's pretty close. That's the Earth's orbit. And instead of heading to Saturn directly at the outer right, we headed into the inner solar system, kind of like a discus thrower, and went past Venus, stole some of the orbital energy of Venus to get us into a higher orbit, and then we went past Venus again. So if you look at the top, this is called what NASA calls a Vivejka trajectory. Now you know what the V and V are. That's you go past Venus once, you go past Venus again, and the E is for Earth. We came back to Earth almost 2 years after we launched, which seems counterintuitive, but those 3 successive flybys gave us enough orbital energy, even though it was not a direct flight, to get out to Saturn faster than we otherwise would. And by good fortune, Jupiter was aligned in such a way that we could fly by Jupiter in the millennium and then have 4 more years and finally get to Saturn. So those of you who are in the academic world can appreciate the fact that as a young professor, the dean was very delighted to know that I was part of the Cassini mission. But they said, okay, when are you going to start getting some scientific results? And I said, well, it's going to take 7 years to design the spacecraft, 7 years to get there and maybe a year or two to take some observations. So the publish-or-perish paradigm for big space missions doesn't work too well. You have to have your eggs in some other baskets as well. It required a fair amount of patience to be involved in a mission where the first return was going to come 14 years after you started. But the launch was successful after 7 years. And as I said, we first headed to Venus. Now, NASA at the time, we were all keen to test our instruments, and I'll be describing the instrument team I was on in a few minutes. We were all keen to test our instruments, but like a parent who gives allowance to kids, NASA said, don't spend all your resources now, because don't come asking us for money later when you finally get to Saturn. So we passed by Venus, we passed by the Earth, and finally we made it out to beautiful Jupiter. Here is Jupiter, and in the foreground is its lovely moon Io, spelled Io, and you can see that it looks different from our own moon. If you look at higher resolution, Carl Sagan called these, the Voyager images of Io, looked like a diseased pizza. That looks so different from our own moon. I sometimes get moon envy when I look at the moons of the outer solar system, because this moon is in an orbital tug of war with its nearby moons and Jupiter, which results in tidal stresses in its interior that produce dozens of volcanoes at any given time. So there's not a single crater that's been discovered on the surface of Io, and that's not because God missed in throwing things around. It's because there's so much erosion that craters get covered up. In the lower right, in that false color, is an infrared image of the dark side of Io as the spacecraft moved away from Jupiter. Absolutely wonderful, spectacular opportunity to take a look at Jupiter as we headed by, but our real destination was 4 years ahead. So that little thumbnail in the sky is Io in the left with Jupiter in the foreground, and we were heading out. And so many people would ask, well, what were you doing for those 7 years between launch and getting to Saturn? And what we were doing was planning what the orbital tour would look like. And that means we had to know exactly, week by week, almost day by day, and minute by minute, where the spacecraft would be and how it would get into a particular kind of orbit. And one of the challenges is you can't carry enough rocket fuel to see everything you want to see. So I'm interested in planetary rings, and one of the worst places to be in orbit around Saturn is in the equatorial plane, because you'd only get an edge view of the rings. So as I once put it, only a moron would go to Saturn and be in the equatorial plane. But the other part of my brain says, well, that's where all the moons are. If you want to visit the moons, you need to be in the equatorial plane. And perhaps you want to be up above to see the aurora in the polar regions. And perhaps you want to be far enough away to see the atmosphere. And so you can't take enough fuel. Some of you might have had a physics class where you spin a bicycle wheel and you realize that as you hold the axle, it takes a lot of effort to twist it. The same thing happens to a spacecraft in its orbit. So we can't take enough fuel to do it, but we used the lesson that we had in getting out to Saturn in the first place of theft, sort of interplanetary theft. We would dive bomb the moon Titan every once in a while, and as we skimmed across the surface of Titan, we'd steal part of its orbital energy and use that as the equivalent of rocket fuel, and that led us into this spaghetti pattern of orbit. So we spent 7 years designing and planning this to try to optimize the science. Well, one of the challenges we had, as I alluded to before, is in order to save money, the Cassini spacecraft, when it was designed, originally had a turntable that was going to allow people to make, to turn the instruments and swiftly switch from one instrument to another. But instead, to save money, they strapped all of the instruments on the side of the spacecraft itself. So imagine you're on a bus, but instead of being able to carry a camera, the camera is strapped to the side of the bus. Maybe your camera is near the left front headlight. Somebody else is near the rear tail light. And you have to tell the bus driver how to orient the bus so you can take a picture of the Statue of Liberty. Not everybody can take a picture at the same time. Furthermore, all of our teams were organized by instruments. And so since not everybody could look at the same thing at the same time, that set up plenty of opportunities for being adversarial. This drew the attention of a sociologist, Janet Vertese, who embedded herself in 2 space missions, the Mars rover mission and the Cassini mission. This book just came out. It's a fascinating look called Shaping Science at how just the organizational structure of these space missions affected how they operated. Because the Mars scientists, we were told, would be sitting around a table, drinking their lattes, looking at a Mars rock, thinking what kind of Ben and Jerry's ice cream to name the rock after, while the Cassini scientists would be using words like fight, wars, battles, because there were winners and losers in decisions on who would be able to look at what we did. But in the end, we finally were able to make a plan. We had the opportunity to be on the far side of the sun from the Earth, and we were able to test Einstein's theory of general relativity by watching the radio signals from the spacecraft get delayed as they passed by the gravitational field of the sun, confirming still today one of the strongest tests of Einstein's theory of general relativity. We finally took a view of Saturn that you can't get from Earth. You can see that the sun is coming from the side here. We're getting closer. And it was about this time, just about the turn of the century, when the Mars orbiter crashed into the far side of Mars because somebody had forgotten to put the units on a table from Lockheed Martin to the Jet Propulsion Laboratory. The table was in feet and pounds, and it should have been in newtons and meters. And that was enough to cause the spacecraft to crash into Mars. And so this was well on our minds after we had had 10 years of planning. None of us wanted to be the ones to have made a mistake. We were getting close to Saturn, and we'd done everything we could. We headed out to the Jet Propulsion Laboratory. Only in California can you have a National Historic Monument for a building that was so recent, but we went out to the Space Flight Operations Facility. As you can see, it's a very welcoming place when you get into mission control. It says, danger, if red lights are flashing, keep out, toxic asphyxiant gas release, or call 911. Well, we'd done everything we could. Finally, we were left with one thing to appeal to, and that was Yoda. Saturn Orbit Insertion Burn, SOI burn. You must find the SOI burn. There is no try, there is burn and no burn. Because if you think about it, the spacecraft had been in hibernation for 7 years. It had gone into the hotter part of the solar system near Venus. We had our Mac Classic computer and our engine. Imagine that you have a car in the garage for 7 years with a computer in the back and keys on the table, and your parents say, 7 years from now, open the garage door, turn the key, start the car, and boot up the computer. Well, we had the same anxiety, but we went out to the Jet Propulsion Laboratory, and our instrument, which is the radio science instrument, was able to monitor the Doppler shift of the radio of the spacecraft to determine that the burn had happened, the spacecraft was slowing down, and finally, after all of those years, after 14 long years of effort, we'd made it into orbit around Saturn. And we had such a spectacular view. I'm interested in a lot of parts of Saturn, but primarily in its beautiful ring system. And if you look here, you'll see there's a tiny little dot to the left, a little point of light. And if you look at about 11 o'clock up at the top, you'll see another tiny little dot inside that narrow ring called the F ring. Those little moons have an outsized effect. They're kind of like the annoying mosquitoes that can disturb a lot more than its own mass. Those small moons sculpt the structure of Saturn's rings in an amazing way. Here are a couple of them. These are 2 moons that share an orbit. They're called Janus and Epimetheus, and they're like Massachusetts drivers in a rotary. neither one can pass each other. They're in so-called a co-orbital state. So when one tries to pass the other, it gets cut off and they switch orbits, and they're constantly doing interplanetary road rage as they orbit Saturn. So it's really a fascinating system. Here's a gap in the rings created by this tiny little moon that you can see on the right called Daphnis. And its gravitational effect on the rings is to make this beautiful wave in the edge. There's just so much structure in the rings. All of these waves, these so-called density and bending waves, are like tightly wound spiral arms of a galaxy. And they're all produced, most of them are produced by small moons. But since the Cassini mission began, we've also discovered that Saturn has its own equivalent of earthquakes. It has internal jiggling or oscillations. Some of you may have heard the term helioseismology, which is a way of determining the internal structure of the sun by seeing how its surface wobbles. And we can do an analogous thing, and the name for it is chronoseismology, named after the god Kronos for Saturn, where there are small waves in Saturn's rings that are literally produced by the jiggling and oscillations inside of Saturn itself. And from that, we can do kind of a CAT scan of the planet and figure out what its internal structure is by taking the pulse of that internal structure by looking at the structure of these rings. So that's a fascinating and completely unexpected result that came from going to Saturn. We see these funny ghostly patterns called spokes on the surface of the rings that can't last very long, because if you look at that kind of smudge at the left, the inner part of the ring orbits faster than the outer part, and that quickly shears out. So these are ephemeral structures changing as we watch. My instrument was called the radio science instrument. You can think of it as one of the world's biggest instruments because it's 1 billion miles across. That has two pieces, the spacecraft and the deep space network on the Earth, represented by this large antenna at the lower right. There are several complexes on the Earth in Spain, California, Australia, from NASA, so that at any given time, one of those antennas is able to see the sky where the spacecraft is visible. And our project was to send the radio beam through the rings or atmosphere, receive it at the Earth, and infer what the structure is. Now, I won't have time to share the results of all of the instruments, but most of you are probably aware that the imaging team gets all the glory because two-dimensional, beautiful color pictures are easily accessible. And the upper image is from the imaging team on Cassini. But we can obtain much higher resolution of the rings by having the spacecraft pass behind the rings, send its radio signal to us, and see a one-dimensional tracing such as the one shown at the bottom. And those are the raw observations that we use to try to reconstruct the orbits and shapes and wave structure of the rings. It's really a marvelous experiment. These are called radio occultations, and it took a lot of planning to find an opportunity so that the spacecraft, the planet, and the Earth would all be lined up at the right time. But Saturn itself is a beautiful planet. This is one of my favorite images where it's a little hard to get a sense for this, but the rings are in the foreground. The shadows cast by the rings are behind. The blue sky and the moon and the limb of Saturn is behind that. And you can think of Saturn as being like Jupiter, the little star that couldn't. It's not quite big enough to have high enough pressure in the interior for the hydrogen that its main composition do each other and produce helium by fusion and to create nuclear energy. So in a way, you can think of these as stars that didn't quite make it, but they're giants nevertheless. They retain some of their heat of formation. They don't have a solid surface. You would parachute forever, descending into deeper, deeper depths. And we had the opportunity to see beautiful cloud and storm systems. Just as a reminder, we have many of these on the Earth. We use up the alphabet in naming the storms, But you quickly use up the alphabet on Saturn if you try to name all of the storms that you can see there. And it's interesting to test our theories of hurricanes by looking at the dynamics of a planet that's somewhat different, where its energy sources are different and it doesn't have an ocean. There's an evil eye at the pole of Saturn. It's kind of a system where the rotation of the atmosphere creates this beautiful system, and it has a polygon around it as well. We can look at the structure of the planet and probe the depths below the clouds by using infrared light, which makes it through the clouds, and also ultraviolet light to see the aurora. So here's a beautiful image of Saturn taken in the infrared, where you get to probe beneath the clouds and see what its energy source is. They're beautiful. Here's this beautiful polar region that I mentioned. And we had the opportunity, which comes every decade or so, to see a giant storm. Here in the Northern Hemisphere, this storm has stretched out so much that it's actually wrapped around the entire planet and come back. It's kind of like a snake eating its own tail. And we can probe the structure and origin and energy of that by looking at different colors. So here we're looking at different infrared colors. And finally, from this long infrared wavelength, we can see where the heat is actually coming from. That's the source of the energy for this storm. It's just an example of how the interdependence of looking at the planet through the eyes of different wavelengths is analogous to looking at stars and the universe with infrared, radio telescopes, ultraviolet telescopes. Each of them gives you a slightly different signature and a different picture of the world. But I want to move on and make sure that I have a chance to talk to you a little bit about Titan, the largest moon, Titanic, of Saturn. This is similar to what the best picture of Titan looked like from the Voyager spacecraft when it went by. And it's a smoggy place. The atmospheric pressure on Titan is actually about 50% higher than the atmospheric pressure in the room where you are right now. But of course, it's much colder. And it was known at the time that it had, from Voyager, that it had methane in its atmosphere, which is a little hard to understand because it doesn't survive long. So there has to be a source of methane. That led to all sorts of fanciful notions that there might be methane seas on Titan. But of course, how do you see them through all the clouds? So Titan was a wonderful target, and the Cassini spacecraft was also named the Cassini-Huygens mission. And here's a picture of Huygens, who was a distinguished astronomer himself in the late 1600s. And among other things, he wrote a wonderful book that I urge you to find from your local library called Celestial Worlds Discovered, or Conjectures Concerning the Inhabitants of the Worlds of the Planets. This is a wonderful book in which he imagines what the living creatures on Jupiter and Saturn and Mars and all the other planets are like. He fancifully thinks about the inhabitants of Jupiter as having a more advanced theories of music than we do on Earth. It's really a very entertaining book. But the mission itself was more serious. It had a probe, and I showed you before an image of the gold-plated, a gold foil covering up the probe that had the Huygens probe that would land on Titan itself. And the plan was for it to be released, to have a parachute. Very great artistic license, I'm afraid, in this fanciful drawing of what the surface looked like. But I keep it because there was the notion at the time that this probe could land in an ocean of methane, had to be able to survive that. And it had batteries that would last only a couple of hours as the mothership flew overhead. So our European colleagues had spent 14 years waiting for their 2 hours of data, hoping that everything would work. So it turned out to be really a remarkable story, because one of the first things that happened on the way down was to see this dendritic river system, but not rivers of water, rivers of methane or ethane leaching out into a sea. And the probe landed successfully. So here on the upper left, you can see those drainage patterns. And in the middle image is the middle and right images are the cleaned up color image from the surface of Titan from the probe. It's a little misleading. Those little cobbles in the front are probably about the size of your thumb. They're a little magnified. But you can do a little planetary geology and realize that rounded structures, surfaces like that, usually are reminiscent of things that get worn down, such as stones in a stream. So we think of this as probably, although these are ice and not rock, examples of things that might have been in some kind of liquid. So we discovered, using the wonderful radar system on the Cassini spacecraft, although Titan is cloudy, there was a radar system which could penetrate the clouds and reconstruct the surface. Astoundingly successful part of the mission. And I alluded to the fact that the spacecraft dive bombed Titan over and over again, multiple times. And there was great contention over who gets to have control of the spacecraft at a given time. But many of them were devoted to the radar experiment, which revealed these northern seas near the North Pole of Titan that you can see here. And one of the open questions was what the composition of those seas would be like. So our team used a clever technique. If you've driven a car into the sun and you see the sunlight reflecting off of the hood, or you're at the shore and you see the sunlight reflecting off of the water and coming to your eyes, that's what we call a bistatic experiment. The spacecraft pointed its radio antenna towards these seas at just the right angle so that if it could reflect off of the surface, it would head to the Earth. And our goal, if the seas were calm that day and the winds weren't blowing, we could see a reflected signal from a 20-watt transmitter a billion miles away. And by comparing the what are called the polarization ratios of the signal, we could infer what was called the dielectric constant, or get a measure of the composition and infer what the material was in these lakes. So we were out at JPL waiting to see whether this would work. And a picture's worth 1,000 words. I'd let you judge whether this experiment was a success. And so we were just looking at the screen. Here's the chief scientist on the mission at the time, head of the mission, clapping me on the back because we had what I've just released is a fistful of dollars because we had a countdown of when we expected to see the signal. And we had just detected Titan's northern seas. It was really one of the high points because you don't usually have an opportunity to get the signal and see it in front of your eyes. All of the images and everything else get processed, but we got to see the signal just as it was coming in. Quite a wonderful event. Well, there are a lot of other surprises that came from the Cassini mission. Here's the tiny moon Enceladus. You get a sense of its size by its comparison to the British Isles here. It's a very small moon, but it looks, again, very different from our own moon. Part of it is heavily cratered. Part of it has very few craters. And just like the moon Io, that's indicative of some kind of process that covers up the craters, some kind of active geological process. But for such a small moon, it was kind of hard to think of what the energy source was. Io has the tug of war of tides of the other moons. And it turns out that Enceladus has the same kind of tidal effect, but in a little diminished extent, with its neighboring moons that produced one of the big surprises. These plumes or geysers of salt water, frozen salt water, escaping to space from the south pole of Enceladus. Well, astronomers become biologists very quickly. All you have to do is say salt water in a billion years, and how many steps can be left till intelligent life. So the NASA space program is definitely want to follow the water. We now know that there's water out there, and somehow there's enough heat in the interior to drive these geysers and plumes. And the spacecraft, we redesigned the trajectory of the spacecraft to fly right through the plumes, and some of our instruments were able to do measurements to determine what the composition and even collect some of the dust grains of that material, that briny material, just several kilometers above the surface. So here's a high resolution picture of the icy surface of Enceladus, kind of looking like an elephant hide, one of the great surprises of the mission. And Enceladus also solved another mystery. There was a ring around Saturn, in addition to the bright rings that I showed you before. There's a very tenuous ring that we named the E ring, but we were prescient because we now know that the E stands for Enceladus, because all that plume material can escape the gravitational field of Enceladus, but it can't escape the mighty gravitational field of Saturn itself. So it's encircling the planet as this dusty, icy, irregular, circular ring coming from Enceladus itself. Well, over the course of the mission, original design was to last for 4 years, but we had plenty of power. We had plenty of fuel to control the spacecraft. So we asked NASA for an extended mission. We called that the XM. And we applied for that competitively and got funding. And then after that, we applied for another extended mission. We called it the XXM for another 5 years. And that was successful. And then finally, we realized that ultimately we were going to run out of fuel. The power from the radioactive thermal generators was going to wear down. And we didn't want the spacecraft to be wandering aimlessly and ultimately land on one of the moons, leaving perhaps some kind of contamination from biological material on the spacecraft. So our plan was to send it into Saturn, and we applied successfully for a final 2 years, which instead of calling it a triple X-rated mission, we called the grand finale. And we had a very audacious plan. We used Titan as the engine to drive us between the rings of Saturn and the planet itself. And for the last 22 orbits, we were able to look at tiny moons like Pan here. It looks like a spaceship or a piece of ravioli. This is a small moon with its own hula hoop ring around the middle. Here's another tiny moon called Atlas that we had a chance to visit. And we used the antenna as a shield as we went through the plane of the rings on that first crossing, because if there was a lot of dust there, we didn't want it to etch the surface of the cameras. And here's an animation of that first fly through that shows us that we were safe. And then the spacecraft turned to start making its final series of observations. So we had 2004 to 2017, roughly half a Saturn year of exploration. Here are all the spaghetti strands of all of the orbits, the fun celestial mechanics, and the design of figuring out how to send a spacecraft to a particular spot. And every minute of that time was dedicated to observations from one spacecraft, one instrument or another, or to send the signals to the Earth. But finally, it was time for us to come to an end. We flew through the gap, and one of the advantages of getting so close is that you can measure the gravitational field of Saturn exquisitely accurately, as well as the magnetic field. Those are ways to learn a lot about the interior. We could also use that to measure how massive the rings were, which is important as a test of how old they are. And after 22 orbits, the next plan was to head into the planet itself. So we took an opportunity to take a picture of home. Here is the Earth and the Moon taken from the Cassini spacecraft with the rings in the foreground of Saturn. Over the last 2 days, we had the opportunity to look at Titan one more time, to look at, to point to Enceladus setting behind Saturn, to look at structures within the rings. And then finally, this was our final image before we headed into the planet itself. So we all headed out to the Jet Propulsion Laboratory to monitor the farewell signal from the spacecraft. And we went into Von Karman Auditorium when the scientists were sitting. I was in the second or third row. And all of the photographers, the paparazzi, were sitting up in front, wanting to take pictures of the scientists as they bid farewell to their spacecraft. And the Jet Propulsion Laboratory left us all with boxes of Kleenex, which I thought would certainly be unnecessary. But when we saw an image of the flickering of the spacecraft signal, it disappeared and then came back, kind of like the last heartbeat in an episode of ER. We really got a sense that things were really over. And the next day, as I was leaving Los Angeles, I went to the Los Angeles airport with my wife, who's also on the Cassini mission. And we looked at the front page of the LA Times that was for sale. And I recognized the purple shirt from somebody on the Cassini mission. And I said, "Who's that bald guy?" She says, "That's you." Because when we lost the signal, I used those tissues. I was just overcome by emotion with a sense that 30 years of my life had been working with colleagues, friends, competitors, engineers, scientists from around the world on a common mission at a time on Earth when there was plenty of contention, the kind of things we're dealing with today. It was realizing that this was going to be the final moment of that close, wonderful collaboration. The Cassini mission gave us a sense of home. Here's the far side of Saturn at the middle, a family portrait of most of the planets, and even our former planet friend, Pluto, in the lower right, Earth and the Moon, giving us a sense of perspective. We're in just of course, this isn't our own galaxy, but it's similar to ours. We're in a remote spiral arm, one of 100 billion stars in the Milky Way, one of 100 billion galaxies in the universe, but it's the only home we know. And I think that the opportunity to study space, to see no political boundaries when you look at the Earth, to interact with colleagues, and to use our ingenuity to learn something about a world nearby is a thrill that I hope every one of you feels when you look up at the sky. And here as we focus in a little bit closer on home, there's a sky view of Vermont. I think they've probably added those lines. And the Middlebury campus, it's great to get a sense of perspective. Welcome home. So thank you all. I'd love to entertain your questions.
Okay, thank you very much. So we're going to open it up for questions now. Some people are posting questions to the chat. That is meant just to address the panelists for tech issues. If you have a question, if you could post to the Q&A window, it is a separate button. It's a little unusual compared to what some of you might be familiar with. And the first question we have is from Lucia, which is, when and how did Saturn's rings form? And how will Saturn and its rings and their composition change with time?
That's a great question, because many and most people thought, I think, before Cassini got to Saturn, that the rings were formed as part of the formation of the planet. But as I mentioned, one of the measurements that we made during the mission was to measure the mass of the rings. And what we discovered is they're much less massive than we'd originally thought. And for a number of reasons, that ends up leading us to a conclusion that the rings are probably more recent than we would have thought, that they may well have formed much more recently than the planet was formed, perhaps even 500 million years ago. So we don't have a complete picture of it yet. We know that they're almost pure ice. But they have, one of the reasons that we think that they're not very old is that the ice is very pure. And yet we know that interplanetary space is constantly being bombarded by micrometeoroids and dust, kind of like putting pepper on a sheet of white paper. And if you grind the pepper grinder, you know how the flecks of pepper will make the paper look darker, but the rings are very, very bright. And so for that and a number of other reasons, we think that the rings are more recent, and that it's probably a competition between being formed by icy moons crashing into each other, and then dissipating. So it's a very active area of research, one of the biggest surprises of the mission, and a great question.
All right, our next question is from Richard, and he's asking, as Juno or other missions are repurposed, can you speak to this as we go forward and follow up missions?
So it's very interesting because it was spectacular to have an opportunity to visit Jupiter at the same time we were visiting Saturn, two giant planets. And the team I was on had team members from the Italian Space Agency who were experts in using the radio signals to measure the gravity of a planet. And they were constantly measuring comparing. At every team meeting, we'd find out what was happening on Jupiter and realize how to first blush, you might think those two giant planets would be very similar. But what we discovered was there's surprising differences in their magnetic field, in their internal structure. And so the other thing that's come about from Saturn, I think, was there are missions such as the Europa Clipper to go to Europa and follow the water. But because the Saturn mission was so successful, there's been a return mission planned called Dragonfly that you may be familiar with, which is going to send a quadcopter to Titan and to try to explore the astrobiological materials on the surface. So I think there are lots of instances where what we learn from one mission tends to inspire other missions as well.
Okay, before the next question, I would just like to remind our audience that any level of question is very welcome, so please don't be shy. Feel free to post them right up. You can also upvote other people's questions. If you would more or less ask the same thing, or you really like their question, you can click on that thumbs up, and that'll bump it further to the top of the list. And our next question is from Claudio, who asks, what is the favorite hypothesis regarding the cause of the Saturnian storms? Might they be the product of some arrangement of gaseous or volcanic activity?
So the basic idea for Saturn storms is that there is upwelling of heat from the interior. You have to find a source of energy for a storm. And on the Earth, we have hurricanes in a hurricane season because we get a lot of sunlight and the oceans are warm. So hurricane intensity on the Earth is, as you may be aware, it's become more intense recently because the oceans have become warm in the fall. A similar kind of process is happening on Saturn. We think that there's an overturning of heat in the interior on timescales of decades that leads to some hot bubble kind of rising up and producing the giant storm that we saw. And because there's so much swirling in the rest of the atmosphere, those smaller cyclone disturbances are also largely driven from heat from the interior. Unlike the Earth, Saturn has a fairly substantial amount of energy coming up from underneath. So even though it's far from the sun, that's an important energy source.
Okay, our next question is from Anonymous with a few upvotes. So you mentioned that the surface of Saturn is not solid. Could you please explain this a bit more?
Sure. Saturn is, the sun is mostly, let me start from the sun. The sun is mostly hydrogen and some helium and a little bit else. Astronomers have a funny periodic table. They call X is hydrogen, Y is helium, and Z is everything else. And that's because there's not much everything else. Now, it's not going to get you through a high school chemistry class, but it might get you through a high school astronomy class. Most of the universe is gaseous. And so when the sun formed, it was a giant gas ball. And in the outer solar system where it was cool and those planets were forming, they formed of the same material that the sun did. Of course, there's rocky material on the Earth, and there's probably a rocky core deep in the interior of Saturn, but most of the composition of the sun is hydrogen and helium, and the same thing is true of Saturn. So it just gets denser and denser the deeper you go. So if you were to parachute into Saturn, it would get hotter and denser until maybe you would eventually get pretty warm, and you might settle in near the interior on a kind of rocky core.
All right, our next question is from Lynette, who asks, does the E-ring actually contain water?
Yes, it does. It's mostly water, and amazingly, we were able to determine before the Cassini spacecraft got there really how big those little water crystals were. But they have a little bit more than water. They have some kind of organic materials. There were instruments on the Cassini spacecraft that let us test the composition of little dust particles like that. So they fly into a little detector and they break apart, and then you use various kinds of instruments such as mass spectrometer to break it apart and use a magnetic field to figure out what its composition is. And they are a strong part of its composition is water.
All right, I'm going to borrow a question that showed up in the chat from my boss, actually, Sarah Dunman, who asks, what did you learn about the structure of Saturn's rings?
Well, I think what's really fun about Saturn's rings are we really think they're governed by Newton's laws of gravity mostly. Newton's law of gravity is something you learn about in high school physics class, and you might think that there's not that much to it. And yet the structures of the rings are amazingly complex and intricate. I think the Saturn has lots of little moons, and each of those moons produces its own spiral patterns on the surface. It's kind of like an etch-a-sketch, and we expected to see those, and they worked out beautifully. I think the thing that I found more intriguing now is that Saturn's rings are acting like a set of ears to listen to the earthquakes inside Saturn. So we're using it as a giant detector that isn't telling us as much about the rings, telling us about it's using that as an opportunity to tell us something really interesting about the planet. There are plenty of mysteries that I wish we understood about the structure of the rings itself too. The rings, by the way, are really thin. If you were flying by, they're only about as tall as a building, a 1 or 2 story building. So they're very, very thin. They're made of ice particles that are from the size of your little finger up to the size of a house or so. They gently jostle each other, and they managed to develop these wonderfully beautiful, mysterious structures.
Right. Our next question is from Nicole, who asks, is it common for moons to be non-spherical, or are most planetary moons spheres?
That's a great question, too. So the one way to look at this is to take a bowl of Jell-O and put it out on a table and ask, how high a mound can you make of Jell-O cubes? And you won't be able to make a pile of Jell-O cubes that reach the moon because they sort of squish out at the bottom. And that's what happens to ice. And that even happens to rock. There's the strength of gravity can be so strong that an irregular structure like that just can't withstand the force of gravity. So if you've seen pictures of asteroids, you can see that when they're hundreds of miles across, they can be irregular. But by the time they get large enough, the gravity is so strong that there isn't enough strength to the material itself to withstand that flattening process that I metaphorically made with a pile of Jell-O. So the tendency is for things to fall down and to become spherical in shape when you become more than a few hundred kilometers in size. So it's a natural process. It's the reason that you don't have cubical planets as well. Great question.
Great. We have another anonymous question, which is, why is Saturn the only planet with rings? Is it due to the composition, location, etc.?
That's a great question, because when I was in graduate school, that was the truth. And I was asked that question on a qualifying exam, and I gave what I thought was a brilliant answer to account for why Saturn was the only planet with rings. And the only thing I discovered was I've spent most of my career since then being proved and proving that wrong. And the only consolation I have is that Carl Sagan didn't know I was wrong either, or I wouldn't have passed. But as it turns out, the planet Uranus has very narrow rings. They were discovered while I was a Cornell graduate student. And because my office mate was one of the co-discoverers, I became involved in that project. So one of the mysteries is, why does Saturn have such broad rings? Uranus has narrow rings. Then we discovered that Jupiter had rings, had dusty rings. I'm the proud co-author of a paper that says Neptune has no rings, followed by, I told you Neptune has no rings, followed by, why don't you believe me? Neptune doesn't have any rings. But guess what? Neptune has rings. It just turns out that they're incomplete. So every one of the giant planets has rings. And we now know that even some of the tiny objects in the outer solar system, asteroids and so-called Kuiper Belt objects, have tiny rings too. And one of the fun things is to imagine how we can look for rings around detect rings around planets. Many of the thousands of so-called exoplanets that we've discovered may well have rings as well. So scientists are coming up with clever schemes to infer the presence of a ring around a distant planet, around another star, even though we'll never be able to see the planet itself. So they're probably more common than we think.
Right. And Alice asks, how does Saturn's gravity affect activity in the rings? Do the rings change shape over time?
Yes, in fact, it's really great. So if you are a ring particle, physicists always have this phrase, a test particle. I always wondered what they mean by a test particle. But if you are, transport yourself to Saturn and plant yourself on one of those little ice cubes, the way you move is in response to all the gravitational tugs of things nearby. And some of those are Saturn, some of those are other moons, and some of those are the material from the rings itself, so the so-called self-gravity of the rings. And so part of what makes Newton's laws so complicated in the rings is that you have to keep into account all of those different gravitational forces, which end up producing spiral patterns that change over time. I mentioned those two moons that are exchanging orbits with each other. Well, those moons produce spiral arms in Saturn's rings that move in and out as those two moons move in and out. And we can see kind of a record, kind of like a seismic trace of the history of those moons fighting their orbits with each other by seeing the past history of those waves. There's another project that we're working on. It seemed unbelievable to me, but we've just discovered that probably that Jupiter was hit by a comet, by comet Shoemaker-Levy 9, and makes you wonder whether Saturn ever got hit by a comet. But we now know, we have evidence because of looking at the ripple structure in the surface of the rings, that on some inauspicious night in 1983, a cometary swarm tilted the rings of Saturn by about 10 meters. And it's taken decades for that to start readjusting. And from multiple sources of observations, we can detect that very tiny tilt and the adjustment of the rings as they wind up in response to that cometary impact. We now know that Jupiter's rings have also been hit and tilted slightly. So these were all kind of the idea that the rings were there forever and that they aren't changing is one of the great fictions. We even have seen a piece of the ring break apart from the outer part of the so-called A ring, and then reaccumulate again. We were hoping it would become a tiny little moon, but it was shy and headed back into the ring system.
All right, I'm going to skip down to somebody who's been waiting for a little bit. Kath asks, what was the composition of Titan's northern seas?
Ethane. The answer is ethane, and with a little bit of methane. And one of the neat things that they were able to do, so the Italian graduate student was on the radar team, and they sent these spacecraft over the oceans. And if you send a radar signal down to an ocean or a lake, you might be lucky enough, if the lake is transparent, to see a reflection off of the bottom. So they were actually able to determine the depth of the ethane sea on Titan by seeing the echo not only from the surface, but also from the subsurface, from the solid material at the bottom. And because they were able to determine that the liquid was transparent, they knew that it was not methane, which would absorb radar. So that was really an extraordinary observation. They are able to determine that they're about like the Great Lakes. They can determine what the volume is. They can even look at what the hydrological cycle is and what the seasonal effects are. It's truly extraordinary.
All right, our next question is one I'm sure nobody on the team has lost any sleep over, which is from Julie, who asks, after waiting so long for the Cassini spacecraft to arrive at Saturn, what tool or measuring device did the team wish it had been equipped with by the time it arrived?
It's interesting. That's a great question. I don't think a lot of us spent much time wistfully wishing we'd done something different. We were so busy with the instruments that we had at hand. Although, having said that, if you're measuring the composition of something, you would love to have a more precise. So none of us imagined that we'd be able to fly through the material coming out of Enceladus. So it would be really great to have an instrument that could do better, more precise measurements of that composition. It would be nice to have a little bit more spectral resolution or sensitivity, but amazingly, almost every instrument worked for its for the entire duration. I went back recently. I came across a folder in my office called Cassini Protests, and I thought it was going to be all about the launch and the plutonium power supply. And there was a big ruckus about whether it was safe to launch a spacecraft with plutonium. But it wasn't. It was from scientists saying, this is such a lousy payload, the Cassini mission's never going to discover anything. And in fact, it's been one of the more successful missions that we've had. So most of the time when people start thinking about what we wish they had, they put their hats on and say, this is a great idea for the next mission. Another good question.
All right, Ron, in several upvotes, asks, of all the new things discovered over the course of this mission, what surprised you the most?
I think, depending on the night you ask, I would say the extraordinary characteristics of Titan. Titan has its own hydrological cycle. It has rain. It has rivers, but not rivers of water. It has sand dunes, probably icy dunes from blown winds. It has lakes in the north. It has seasons. It has an atmosphere that's dense enough so that it has clouds. So it's its own sort of world that has, and the lake system was so surprising as well. So Titan certainly stands. But then the fact that other moons have been discovered to have undersurface oceans. Titan has an undersurface ocean. By looking at the gravitational fields, seeing how different the satellites are from each other, even though they live in the same vicinity. I think every scientist who was involved when Saturn had been asked the question for those 14 years, what do you hope to find? And the answer I always gave was, I can tell you what I hope to find, but I hope I'm wrong because nature is always more exciting and imaginative than I am. And it's true. The things that have kept me excited over the last few years since Cassini has crashed into Saturn are the things that I never imagined would be there, such as the listening to Saturn's heartbeat. So it's full of surprises, and that's what makes science so much fun.
That's an excellent segue into our next question, also from Anonymous, which is how much data that was sent back still remains to be analyzed and understood? A
lot. But I think one thing that's been done for this mission, it's kind of a scandal. But if you try to go back to, for example, the Voyager mission, which was that beautiful grand tour of Jupiter, Saturn, Uranus, and Neptune, and you try to go back to the raw data and the raw computer programs, many of those observations are just plain lost. They weren't archived sufficiently. And so the Cassini mission, a lot of energy went into making sure that the data are preserved. I have my own team spent 3 years writing software that we've put on GitHub so that future scientists can analyze our complex observations. So I mentioned that we make these measurements, we send the radio signal through the rings to the Earth. And the part that I didn't mention, which is a little technical, is that it creates what's called a big diffraction pattern, lots of fringes. And in order to get that exquisite structure of the rings, we need to remove the effects of diffraction. But that's an enormously complex process. So I hired 3 students between undergraduate and graduate years to write open source software and put it on GitHub so that future generations of scientists will be able to go from our raw data to those beautiful ring profiles. And almost every other instrument is doing the same thing. It's just an unbelievable source of richness that I think is going to keep people busy for decades. I hope so.
I'm going to skip down to somebody who's been waiting for a bit as it segues with the grand finale. Sean asks, did the spacecraft burn up when it entered Saturn? Emphasis on burn.
Yes, it did. It was flying very fast. It was interesting. What we could see as the spacecraft was headed into the atmosphere, we had that big dish antenna pointed towards the Earth. And that antenna had 3 different wavelengths. And each of those wavelengths, radio wavelengths, had an antenna beam that was detectable for a longer or shorter period of time. And so on the screen, we could see these little pulses of light, pulses of signals from each of these individual radio beams. And we could predict which one we expected to disappear first. So what finally happened was, as the spacecraft got deeper into the atmosphere, the so-called attitude control jets, the little thrusters on the spacecraft, were not able to withstand the atmospheric pressure that was causing it to twist to a side. And the antenna could no longer be pointed towards the Earth. So you'd lose the signal for a little while, and then it would come back. It was kind of like hoping a patient would survive. We could see these little pulses flickering and going. But it was moving so fast that ultimately it just slammed into the atmosphere, just like something from outer space burning up in the Earth's atmosphere, and it just disintegrated.
Okay. Next question on this topic is from Vicky, who asks, what can be done to shorten the interval of spacecraft conception and spacecraft launch such that the technology is not obsolete, presumably by the time it gets there?
Those are great questions. One of the challenges is that even though I showed you that picture of the galaxy and our own neck of the galaxy is not very big, 1 billion miles is a long way to go. So the Pluto mission got out to Pluto much quicker than we got out to Saturn. But you'll remember that it didn't get into orbit around Pluto. It didn't carry enough mass to have enough rocket fuel to be able to stick around. That's a tall order. So in order to have an orbiter mission, You have to be able to carry the material to put the brakes on. So exploring the outer solar system is just an intrinsically slow process. So just in a couple of weeks, you'll have the opportunity to see the flotilla of Mars spacecraft, one from the United Arab Emirates, one from China, one from the United States, literally just in a little more than a month. 2 landers, Chinese lander and the US lander, are scheduled to be there. The US has a little helicopter it's going to fly. Getting to Mars, designing a Mars mission and getting there is really quick. So the inner solar system, you can be much more nimble about. The outer solar system, we just face the fact that there isn't any propulsion system that's going to get you there in less than a few years. The other thing is that in order to, spaceflight is expensive. And so showing that you can use an instrument that's already been used before is a way of making it cheaper, but it also means that you don't necessarily have the cutting edge technology. So it's always a challenge to find a balance between those two. So I think everybody would love to find a way to get there faster. But the gestation period is really long for these outer planetary missions. And you can see on the astronomy side of things too, look at how long it's taken the James Webb Telescope to be designed and to get ready for launch. I'll be crossing my digits, as every one of you will be too, when that launch finally happens. But the planning stage for that to launch is really enormously long as well. It's just a complex undertaking.
All right, we have more questions, but I do want to pause just for a moment to give Dr. French a moment to catch your breath. And also to say that we will be posting some links in the chat for our attendees where you can find the mailing lists for the Middleman Observatory, Silvera, and the Perkin Observatory. So to receive information on the next installment of this lecture series, as well as a variety of other events put on by all 3 organizations, you can follow those links and please sign up for one or all of them.
So let me give everybody permission to disperse if you want to, but I'm also so impressed by your questions that I'm happy to stick around and answer some more. But thank you all for spending part of your evening with me and learning a little bit about what it's like to explore our beautiful solar system. And I hope that you will take advantage of the clear and dark skies that you have in Vermont and New Hampshire to let some of those photons shine on your retinas yourselves. Get that wonderful experience of seeing what those planets are like. Jupiter and Saturn aren't too far apart these days if you get out at the right time of night. So thank you all for listening, but please do stick around because I'm happy to answer more questions.
Okay, our next question is from Colin, and right on topic for things you could possibly see with a small backyard telescope, is what exactly causes these enormous Saturn storms? Why are they so rare, and how do they, quote, spread?
So we think they're rare because it takes a while. There's it turns out that so-called atmospheric dynamics, thinking about climates on other planets, is almost as complicated as on the Earth. The Earth is complicated because the oceans make life complicated. The circulation of the oceans and the way they absorb heat and the cloud systems and the sources of energy make it really hard to predict climate from one year to another. And the same kind of thing applies to the outer solar system, where, as I mentioned before, the internal sources of energy, the sources of heat, seem to take a while to well up. But it's a notoriously difficult kind of physics problem to predict. It's kind of like predicting when the next earthquake is going to happen. It's a little hard to know. You can get an estimate of what the timescales are, but challenging to know precisely. But they spread in part because there's no solid surface, and the planet, each latitude of the planet rotates at a slightly different speed, just the way the sun does. The sun rotates in about a month, but parts of it spin faster than the others. That ends up having an interesting effect on sunspots and the sunspot cycle for the sun. It has an interesting effect on Jupiter and Saturn, too, as these so-called belts and zones, swirl relative to each other. One of the reasons we like to learn more about the gravitational field of the planet is it lets us learn something about how those storms and circulations actually develop. Those are still, unfortunately, still open questions, but I think we have the data in hand to give a lot of graduate students some time to be thinking about it for the next decade.
Okay, to respond to a tech question, the recording of this talk will be posted on the Midland Astronomy YouTube channel if you'd like to rewatch it or to share it with family and friends. And I imagine we can probably beg for a link to show up in chat in just a moment. And in the meantime, the next question is from Kat. Expect down the road a manned flight will go explore around Saturn?
I'd love to think so. I have to take my vitamin E before that happens, but there's a lot. I have friends who are involved in human spaceflight, and I have friends who want to go to Mars, but we're about to see what amazing things can be done on Mars with rovers that are much less complicated than sending humans, and much less expensive. So my own view is that Saturn's a bit of a reach. The inner solar system is more accessible. I hope that some of you younger folks online will be around when we head out to Saturn. But for me, I think it's going to be part of science fiction.
All right, our next question is an interesting take from Nicole. And her question is, as a sociologist, I'm interested to know if you learned anything surprising about the way you worked with others on the team when you read/shaping science.
I love that question because most scientists are not, let me put it this way. I'll put it succinctly first. I began to understand why peace in the Mideast is so hard. And let me explain what I mean. What's really interesting about that book is it points out that because of the organizational structure into teams around instruments, which is based on how the spacecraft was built, rather than on scientific disciplines. I'm interested in rings. There were people on other instrument teams interested in rings too, but in many ways, we were fighting with each other rather than cooperating because not all of us could observe what we wanted to at the same time. So there was kind of an uneasy piece between wearing your science hat and wearing your team's hat and wearing an engineer's hat. The thing that I discovered is that although scientists aren't trained to be diplomats, there were some who became more adept at it than others. An argument that doesn't work is to say, my science is better than yours, because that argument gets turned on its head to you very quickly. Let me just tell you what a typical day was like when we were planning our observations during the mission. We would be planning the details of what would be happening in 6 weeks. And around that table would be all of our collaborators with different instrument teams trying to make sure that everything works. In the afternoon, we'd be fighting for time on who's going to be observing something a year from now. And the people who are our colleagues and collaborators in the morning's meeting would be our adversaries in the afternoon's meeting. And then in the evening, we'd have a social event where we're all trying to get together. So you discover that you have to find a way to compromise, to settle your differences, to acknowledge that somebody else's point of view has some validity and that you're not going to win every argument. And the teams who had leaders who were unwilling to countenance that somebody else's science was better than theirs resulted in some dysfunction. And I haven't seen how honest and straightforward Janet is about some of those teams, but those of us on the mission, it was not hard to witness and to acknowledge that some teams work better than others. I think, for example, how openly you share data with another team. My own view was this is the public's mission. It's not our personal mission. And I eventually became the leader of our science team when our original science leader retired. And my view always was our data are your data. many scientists say, I spent 14 years getting this, let me at least publish first. And my view, in part, was we'll have plenty of chance to publish together. Let's get the best results out. So I learned a lot about negotiating skills and acknowledging that other people have good ideas, even if you don't like them. I think that's one of the great lessons of science. I mean, how many times, especially recently, have you heard a political argument where somebody said, that's a good point. I never thought about that. I better take that into consideration. But in science, every scientist is wrong at some point, even Einstein and Hawking. So learning to be wrong and to acknowledge that other people are right is a valuable skill that I wish we could be transferable from science to other realms. So I love thinking about the sociology of science, and I apologize for the long-windedness of my answer.
All right, our next question, as we were in the meta, also from Anonymous, is with what you learned or observed from this mission, what impact has it had for life on Earth, technology or quality of life improvement, etc.?
I think probably the direct spin-offs. I mean, we didn't go to the moon to invent Teflon, even if Teflon came from going to the moon. My own sense is there's the international scope of the mission, the opportunities to see the Earth from a different point of view, to share, as Cassini did a lot, to try to share in public outreach, to get kids interested and involved in science was, I think, one of the big payoffs. There was a day where the instrument team leader for the imaging team had everybody go out and wave at Saturn one day, and the spacecraft took a picture of the Earth. And there was a montage of all the little pictures of people waving to Saturn at that same time. It just is a time when the Earth craves an opportunity to feel like you're a part of humanity. I think that's one of the hallmarks of the Cassini mission.
Okay, we have 6 questions left. Kath asks, is Saturn changing? I observed it in 1989 in the Badlands, South Dakota at a ranger's telescope.
So its aspect changes. You can see the pictures from the Hubble telescope behind me. Its aspect changes. The opening of its rings changes from the Earth over the course of its 30-year orbit. So you can see it looking edge-on compared to more wide open. So that would be the most visible change that you'd see as you look from the Earth. The actual pattern of how bright the bands are changes moderately the way it does on Jupiter. But mostly it would be the appearance of the rings that you would see that would look so different.
Okay, our next question from Kale is, why are the divisions between the rings of different size, some wide, some very narrow?
Oh boy, this is it's one of the most obvious questions you'd ask, and it turns out to be one of the hardest, because there is no simple. Although we do know that some of the edges of the rings, like that one you can see, the dark band is called the Cassini division. And the inner edge of that happens to be orbiting at a point where the moon Mimas orbits once for every time a ring particle orbits twice. So that's called a resonance. That's a magic spot. But why the gap is as big as it is still kind of mysterious. But usually when there are gaps in rings, they're associated with either tiny moons that are embedded in it or bigger moons from outside that have that tug of war that I alluded to.
All right. Fine. They're from Dale and Claudio. The first part is, how much of the information obtained by the mission has been studied so far? And that can segue into what future plans exist for the return missions to Saturn and Titan.
Okay. So I would say that every instrument team has done a pretty good initial look at their observations. But usually what happens in something like this is that you For example, there are, I don't know, probably 100,000 images of Saturn's rings that have been taken. The imaging team has looked at probably a few thousand. They've taken the highest quality ones, but there's a lot of information left in those other images. And we get a sense for how this works by scientists who are going back to the old Voyager data and realizing that there's information from the Voyager images that was never extracted from them. So my own sense is with the more digital technology that we have now, the better archiving, the better data mining techniques that we have, the more powerful computers we have, and the accessibility of the data are going to make it possible to make connections between instruments that weren't possible before. So if you work, there's a planetary data system at NASA which tries to integrate the observations from lots of different instruments. So it used to be really hard if you wanted to compare an ultraviolet observation and an infrared observation. It's much easier now, and will be much easier, to say, I want to see what that part of the moon looked like on a particular day from a particular instrument, put all the results together. And I think there are good open questions to be answered for decades. And then the second part of that question was, how does that inspire future missions? The NASA has what are called decadal surveys. We're just hitting a decade now. So Astrophysics is putting together its big questions for the next decade. The planetary community is also putting together the big questions for the next decade, which include recommendations for what the next planetary missions will be. So I think the release of that will probably be in about a year, but that will reflect the consensus of the professional scientific community about what the big open questions are and the priorities that we should have in funding them for the future. So keep your eye out on the web pages for those decadal surveys, because they will probably be mentioned in Sky and Telescope and Astronomy. It'll give you a sense for what the future science is going to be.
Okay, we have one more question. Bruce has waited quite a while for this. I saved him to the end. I hope he's still here. Bruce asks, did you know Donald Arabian, who was the head of the mission evaluation room for the Apollo mission? He was my mother's cousin.
I wish I did, but I will tell you that when I went out to the Jet Propulsion Laboratory and met so many hundreds of engineers, I came to a deep appreciation for their commitment to the mission. You know, the scientists are the front line of a mission. You can publish something, you can give a talk, you can show the pictures, but none of that comes without all of the complicated mission planning, the engineering tests, even the political agreements on being able to use the nuclear power. I've given talks to retirement communities, and when at the end of every talk, there's almost always somebody who comes up and says, one of them says, I used to work for Kodak and I designed the heat system for the Hubble telescope, or my uncle was involved in the radar system for this mission. It's just, it's very heartwarming to have those connections, because being part of space is something that even today you can feel such great pride in, whichever connection you have. So I appreciate that question. It gives me a chance to recognize all those people doing that great work.
Okay, one more question came in. And then after this, if it's okay with you, Dr. French, we can allow people to raise their hands. They've stuck around this long.
Sure.
If you'd like to raise your hand, we can unmute you. If you'd like to ask a question with your own voice or make a comment or a statement, now would be an excellent time to do that, if that's okay with you.
Sure.
Okay. And our last question that is typed is from Annette, who asks, were all the images stills, and is it possible to stream imagery?
So the one thing to keep in mind is that when you're at Saturn, it's actually pretty dark. You're 10 times as far away from the sun as the Earth. And because of what's called the inverse square law, that means it's 1/100th as bright, 1% as bright. One of the reasons we didn't take solar panels out there, because they would have been needed to be 100 times as large as the Hubble telescopes to produce the same amount of power. So you need to have exposures that are sometimes fairly long. And each camera picture is usually taken with a different filter. They aren't usually used for color. So you would make sequences of images with different filters. You'd rotate the filter wheel and take a different image. And then you can put together time lapse. So there are certainly some wonderful images that are sequenced together to show time lapse of moons passing behind the rings and things like that. But in terms of what we normally think of as movies, nothing really is quite the same. It doesn't move at quite the same pace.
Okay. So I don't see any hands raised, but two more text questions came in. Alice asks, how much are you actively involved now in plans for future missions?
Well, I'm involved. I'm always reviewing proposals. So as somebody who's been involved, one of the complicated parts I discovered from the Cassini mission and also from the Hubble Space Telescope is finding somebody to render judgment on which mission gets chosen, because there are so many conflicts of interest. When the Saturn mission was proposed, anybody who could spell Saturn was a scientist involved in the mission. So we ended up, even those of us who put in our own proposals were on the review panels. So they had this complicated web of conflict of interest proposals. This is one of the advantages of teaching at a place like Wellesley, because there are no other scientists on the faculty who are submitting proposals. If you're at the University of Arizona or Caltech or MIT and you put in a proposal, nobody from that institution is supposed to review your proposal. So I'm constantly getting hit up because I don't have conflicts of interest with anybody else in my own community. So it gives me an opportunity to participate in that process. I was on a losing Pluto proposal. I think they chose the right one. It involves an enormous expenditure of time to be on some of these mission proposals. And at the moment, my hands are so full of analyzing the data we have in hand, I'm not involved. But I'm greatly interested in helping to shape what the new missions are going to be like.
All right, Alex, I see your hand up. Would you like to unmute yourself and speak?
Hello, Dr. French. First, I want to say thank you for spending your time and telling us about your experiences with the Cassini mission. This has been really, really cool to hear about. I'm curious, how exactly what was it like? How did you end up working on the Cassini mission? I mean, you must have submitted a proposal and such, but how did you figure out oh, this is something I want to do, or what kind of, who do you have to talk to, sort of,
Great question. So I didn't have a chance given the limited time, but it's an interesting story because I had been involved in the Voyager project during the second half of the mission, because I was involved in the study of the Uranian rings, and Uranus was a target. And so the Voyager spacecraft, the Voyager teams were very interested in knowing what the latest results were about the Uranian rings. So I got to know people, got to go out to JPL, meet some of the scientists who were on the Voyager mission. And one of them had, by the name of Lonnie Lane, was on an ultraviolet instrument. And when the Saturn mission got proposed, he and some of our colleagues had the ideas of putting together a special ultraviolet instrument for the Cassini mission. So I became a participant in that instrument proposal because I knew those people. I worked on it for a year, and then I went out to Cornell, where I'd gotten my degree, and my collaborators were, to put the finishing touches on the proposal. And a member of my thesis committee said, "Great proposal, Dick." I said, "Thanks, Joe." And he said, "It's never going to get funded." And I said, "Well, it would have been nice if you told me that at the time. Why not?" He says, "It's too specialized an instrument." So I looked a little crestfallen. He said, "Well, you can still be on the Cassini mission." I said, "Well, how's that?" He said, "Well, you can put in a proposal to be on the science team for for an instrument that's already been a facility instrument that somebody else has already built. I said, but Joe, the proposals are due in a week. And he said, stop complaining, start writing. So the story I don't like to tell my students is the term paper I wrote the night before that got the A. When NASA called, they said, sorry about that instrument proposal, but welcome aboard on the radio science team. So I, from very good fortune, got told that there was an opportunity to be on the Cassini mission that I hadn't even been aware of until he mentioned it literally a week before the proposals were due.
That's very impressive. Thank you.
Thank you.
It looks like our final question is from Julie again, who says, that's a good one. How many people were on the Cassini team?
Oh, so there were 12 instruments. Each science team had probably a half a dozen or a dozen. But then there were hundreds of engineers at the Jet Propulsion Laboratory, and then also at the universities and other sites. So many hundreds in the end who were involved. Not everybody full-time. When you're at the Jet Propulsion Laboratory, you're often working at several missions at the same time. We discovered, interestingly, that I almost felt like an astrologer when you hear about when Jupiter's aligned with Mars and all of that. Well, it turns out that when Saturn is aligned with Mars, that's a bad thing, because that means that the antennas on the Earth that can listen to Mars spacecraft are the same ones that can listen to a Saturn spacecraft, and they can't listen to both at the same time. So then you have extreme competition for what's called deep space net time. So during those moments when Saturn and Mars were aligned, I found that my friendships with my Mars colleagues were sort of cooled a bit as we had our contentious fights over who would get the. You go to all this effort to make the measurements, but they're no good unless you send them to Earth. And since Saturn's so far away, it takes a while to do that.
Okay, I don't see any other questions, so this is your last chance to raise your hand to speak or to type something in.
Well, let me just thank everybody who might still be online to say thank you very much for sticking around. Even though I can't see your faces, I'm really grateful for your attendance, and it makes me feel less isolated as I sit here in my home office with only Saturn behind me.
Okay, we do have one raised hand. Kath, go for it. Okay, we might have some technical difficulties there. So going once for any other questions?
I'm happy to answer a written question if she can do that.
Oh, sure. Kath, you want to take a moment to type out what you wanted to ask? Anonymous has suggested that this is not a question, but that you have his vote, or their vote, excuse me, for the commander of the Space Force.
Well, that's very sweet. Thank you all. I taught Astronomy 100 this last semester remotely to 45 students, and I structured the course as though we were on board the crippled Enterprise going out to the TRAPPIST system of 7 planets where each of the students went to a different planet. So that was the closest I've come to being the commander of a space flight, but it was very rewarding too.
Okay, well, I don't see anything else coming in. So that will conclude our talk for tonight. I'd like to thank Dr. French for speaking to us and for fielding all of our questions.
Thanks, everybody.
And I'd like to thank our panelists for putting this all together, and especially for our attendees for joining us and asking so many good questions, and especially for the diehards who have stuck around this long. Once this meeting ends, you'll be automatically redirected to an online survey, and it would be very helpful to us if you filled it out so that we can continue to improve our events and understand who these talks are reaching so that we can keep fine-tuning and growing. That page will also contain links where you can find the websites and mailing lists for the Midland Observatory at Middlebury College, the Southern Vermont Astronomy Group, and the Perkin Observatory at Dublin School. Thank Thank you all very much for joining us, and I hope you have a wonderful rest of your evening.
Bye, everybody. Thanks a lot.